evening and welcome to our honorable speaker, Dr. Subhadeep Halder, our patron, Dr. Urmila Ukil, the principal of Sarojini Naidu College for Women, Dr. Sudeshna Chatterjee, the coordinator of IQAC of our college, Dr. Mala Bose, the head of the Department of Zoology, all respected colleagues and dear participants. So it gives me great pleasure to welcome you all to this webinar we have organized on understanding climate change on the occasion of the World Environment Day. So climate change is a word that we keep hearing nowadays very often, and we can say with certain confidence that it is a fact that we cannot deny. Although there are people who do not believe in climate change, and we can say they are kind of climate change deniers. But given the body of evidence that exists, I believe that we cannot deny the fact that climate is changing. And you must be knowing that it is believed that due to the actions of humans, the pace of climate change has accelerated over the past century or so. And so it is very important to increase our understanding and awareness on this issue. And various models have been built to predict and quantify climate change, but there have been various challenges associated with each model, which makes it difficult to predict the precise extent of climate change, especially over a short time span. So today we will learn about climate change modeling and the challenges associated with it from Dr. Halder. So it is our privilege to have him as today's speaker because he is a very active researcher in meteorological phenomena related to climate change. So on behalf of the Department of Zoology, once again, I welcome Dr. Halder. And now I would request our chief patron, our honorable principal ma'am, Dr. Urmila Ukil, to kindly deliver her remarks.
Aniruddha, I can't hear you. I can't hear you. Can you hear me?
Yes, I can hear you, ma'am. You please give your address.
Can you hear me?
Yes, we can hear you.
We can hear you, ma'am.
If you can switch off your video. Ma'am, we can hear you.
Can you hear me, ma'am?
We can hear you, ma'am. We can hear you, ma'am.
Actually, Aniruddha has requested you to speak about this webinar for a few minutes. Telephone.
কাবেরী
দিদি বলুন কি বলছেন?
Yes, ma'am.
শুরু করবে?
হ্যাঁ ম্যাম, আপনি শুরু করুন, আমরা শুনতে পাচ্ছি।
আমাকে কি শুনতে পাচ্ছো?
হ্যাঁ ম্যাম, আমরা শুনতে পাচ্ছি, আপনি বলুন।
বলছি শুরু করবে কি?
হ্যাঁ দিদি
ম্যাম, আপনি স্টার্ট করুন, আপনি বলুন।
মানে আমাকে কি বলতে বলেছো?
হ্যাঁ ম্যাম, আপনি বলুন, আপনাকে বলে দেওয়া হয়েছে।
তোমরা কি আমাকে শুনতে পাচ্ছো?
হ্যাঁ ম্যাম, আমরা শুনতে পাচ্ছি, আপনি বলুন।
ওকে থ্যাংক ইউ কাবেরী। respected colleagues, esteemed guests, and the participants, and my dear students. A very good afternoon to all of you. It gives me immense pleasure to welcome all of you to the one-day national level webinar on understanding climate change, organized by the IQAC and the Department of Zoology of Sarojini Naidu College for Women, Kolkata. I thank all the members of IQAC and the Department of Zoology of our college for organizing this webinar. On behalf of the college, I express my deep gratitude to the Honorable Speaker of today's webinar, Dr. Subhadeep Halder, Assistant Professor, Department of Geophysics, Institute of Science, Banaras, Hindu University, for spending his valuable time. Today, on the occasion of World Environment Day, it is time for all of us to take stock of what we have done to the natural world in our bid to advance human civilization. Natural disasters have now become the norm as we battle the reality of a changing global climate. As the theme of this year suggests, we have only one Earth, and it would endanger our own survival if we tip its natural balance towards destruction. Therefore, it is imperative to concentrate our efforts towards a careful preservation and protection of the environment and rebuilding what we have owned down. Our not so distant future depends upon it. To that effect, it is pertinent to know all the aspects of climate change and how it is brought about so that we may do our bit. With this intention, we have organized this webinar so that all of us may be well informed about the subject. I believe that we will be greatly enriched by the deliberations of our learned speaker. I wish this webinar to be an enjoyable webinar. I thank all the participants of today's webinar for being with us today. I again thank our learned speaker. Thank you all once again. Thank you.
Thank you, ma'am, for your encouraging words and your remarks. So next, I would like to request Dr. Sudeshna Chatterjee, the coordinator of IQAC of our college, to kindly give her remarks.
Thank you, Aniruddha. Respected Principal Ma'am, Dr. Urmila Ukil, our Honorable Speaker, and other participants, on behalf of the IQAC, I welcome you all in this webinar. Actually, this webinar is very important in its content and for the days to come. However, today being a special day, being a Bengali, today's significance in the Bengali society. Not many have attended this webinar. And on behalf of the organizers, I am very sorry, but we are recording this, the whole this process, and it will be available in our college YouTube channel. And I hope that we can make our students watch this, listen to your valuable speech, and apply this in their daily lives. Already Aniruddha has said about the word climate change, which I am listening since the last, in my adult days. since the last 40 years. And in the 21st century, this has been accelerating so much that I am very afraid that our next generation, they won't know what is an Arctic cap. And the Amazon is already one-third gone, I'm afraid. But the powers, that the political leaders that are in power, they don't care, they don't bother. So the onus is with us, the people, and our future generation, who has to bear these Herculean tasks and to know an enemy, to fight an enemy. The best way is to know it. So I am hope that my dear colleague, very junior to me, but in his knowledge, he is far superior to me in this field. I hope that he will guide us how to fight this great danger and how we can make our next generation aware of this danger, and we will stand united to fight this. With this, I welcome you, and I once again, I hope many of our colleagues will join consequently. Thank you.
Thank you, ma'am, for your remarks. So before beginning the talk of Dr. Halder, I would request Shangomitra to briefly introduce the speaker to our audience.
A very good evening to all of you. Today, this task of introducing our very prolific and generous guest of honor is a real great privilege for me. Well, Dr. Subhadeep Halder is presently holding the designation of Assistant Professor in the Department of Geophysics, Institute of Science of Banaras in the university. Prior to this, he was Assistant Professor in K. Banerjee Center of Atmospheric and Oceanic Studies, University of Allahabad. Before that, he also worked as Scientist C in the Extended Range Prediction Group of Indian Institute of Tropical Meteorology of Pune. Coming to his academic qualification, he graduated from Ramakrishna Mission, Narendrapur. In physics, he pursued his MSc from BHU, MTech from University of Pune. He received his doctoral degree from Indian Institute of Tropical Meteorology. He also has a vivid research career. He was a CSIR NET Fellow in IITM, a postdoc research scientist in Center for Ocean, Land, Atmospheric Studies in George Mason University of USA. He also authored and reviewed a large number of research articles in big publication houses, delivered invited lectures in very high-end international conferences. Beside this, he headed several research projects under the aegis of DST Serve, etc. Not only that, he also supervised a number of students quite successfully. His research areas interest mainly hovered around climate predictability, variability of monsoon, severe convective phenomena, among others. He was also conferred with numerous awards, some of the remarkable ones being Young Scientist Award 2019, Outstanding Student Paper Award in AGU Fall Meeting in 2015, UGC BSR Research Startup Grant Award. Beside his academic career, he was also an integral part of administration sometime. Today, he's here to share an energetic, informative, and interactive session with us. Without further delay, I invite him to this virtual forum. Thank you, sir.
Thank you, ma'am, for the nice introduction. I don't know whether I deserve such vivid applause at this level. There are a lot of things to be achieved. However, I would also like to thank respected Principal Ma'am, Dr. Urmila Ukil, respected Ma'am from the IQAC cell, the organizers, and Dr. Anuruddha Mitro. I would like to express my thanks, and I'm happy also at the same time for the organizers giving me this opportunity to share some of my views with the students and the academic fraternity at large. So without taking much time, I'd like to straight away start presenting. So just give me a few seconds. Just a few minutes. I think I am facing some technical issues in sharing my screen. I think there are some technical issues, software related issues. So I would like to just log out and join again using a different laptop so that there is not much delay.
Okay.
Hello. Can you hear me, Aniruddha?
Yes, we can hear you. Please
Okay.
go ahead.
Okay, so I'm starting. Can you see my screen?
Yes, sir.
Okay. So as you can see that the title of the present talk is to understand the science and challenges in the modeling of climate change. So this is a brief outline where I'll try to discuss what is climate change, the difference between weather and climate, what actually determines the Earth's climate, and what are the technicalities of modeling climate change and what are the complexities involved. So this is a particular figure which has come out recently in 2021 in the Intergovernmental Panel on Climate Change report, AR6, that is the sixth assessment report, and it shows the change in global mean temperature in the last 100,000 years. So in the left, the figure on the left shows the observed temperature from 1850 till present and reconstructed temperature before that. So what we see here is the unprecedented increase in global mean temperature after 1850. And when we zoom on this, what we see, so when we zoom, we see that there are two curves. So one that follows almost a straight line, which would say the business as usual. That is the shaded lines in green, and the other one is the orange that increases upwards. So here the black curve shows the observed mean global temperature. And what are these shades? These shades are simulations from multiple climate models. And these shades in green are also the same from multiple climate model simulations. So what is the difference? So it has been shown that if only natural forcings are kept in the climate models, so natural forcing means solar forcing and volcanic forcing, then it was found that it would have been business as usual and the temperature variations would have been normal. Around these are basically departures from the long-term average, so that they would have been around 0 if there would have been only natural variations or natural forcings. However, when anthropogenic factors are included in the models, say that is both natural and anthropogenic factors are included, then the climate model simulations are able to replicate global observed mean temperatures. So this particular diagram clearly showed, again, yeah. So it clearly showed that the observed global mean change in temperature, surface temperature of the Earth, is as a result of natural changes as well as anthropogenic factors. Now, here are the few plots which shows what is the global spatial distribution of increase in temperature. So the top left is observation and the right is simulated change. And what would be the global mean temperature, global temperature distribution under a global warming of 1.5 degrees centigrade, 2 degrees centigrade, and 4 degrees centigrade. So what is shown here is really an alarming scenario. And this particular panel at the top shows the global change in precipitation distribution under a 1.5 degrees centigrade warmer world, 2 degrees centigrade, and 4 degrees centigrade warmer world. And associated with that, what would be the changes in soil moisture distribution? So one important fact is that it is said that the wet gets wetter and dry gets drier. So the regions that already have a monsoon-like system or heavy rainfall during the summer season, they show an increase in rainfall in the future warmer climate. But also the drier regions also show an increase in variability. For example, the Sahara Desert and some parts of, say, Pacific Ocean, and decrease in variability over the Atlantic Ocean. And associated with that, there would also be hydrological changes, which has huge ramifications for the agriculture and hydrologic sector. So, how do we assess climate change? So, a variable like temperature, say if we take daily, a monthly, a seasonal, or annual temperature, and if we have, say, 30 or more years of data, and if we calculate the values, let us say if we subtract the value from the long-term average and plot, so we would get an inverted bell-shaped like distribution, which is called a normal distribution. Statistically, it is like normal distribution. So what does it show? That the peak at the center indicates the mean, and the tails on the both side indicate the extremes. So if there is a increase in the global mean temperature, then the mean value would shift to the right, and associated with that, the tails would also move. So it means that the hotter days or hotter months or seasons or years would become more hot, and the colder would become less cold. But the change in climate could happen in both ways, either through a change in the mean or through a change in the variance or standard deviation. So either there could be a shift, that is, the entire bell is shifted to the right, and it's like there is a change in the mean value as well as the extreme values. And if there is a decrease in the number of values having closer to the mean, so that means the variability, that is the measure, it is a measure of the randomness or the how many extreme values we have. So if it becomes more flat, then that would mean hotter days or months or seasons would become more hot, and colder days or months or season would become more cold. And if both happen together, that there is a change in the mean as well as the variance or standard deviation, then there could be a shift in the mean temperature, and there could be a different type of variation in the extremes. So change in this climate or change in this distribution could happen in all these ways. So this figure shows what is the, so let us first try to see what is the global, what do we understand by a climatic distribution. So if we look at global precipitation in summer, shown in the lower panel, and in winter in the upper panel, so it shows that there is a band of high cloudiness and precipitation in around the equatorial region, that is within the tropics, and the Indian monsoon region is also a part of that. And during the northern hemisphere winter, this precipitation band moves to the southern hemisphere, and basically this movement is as a result of the movement of the position of the sun around the equator, that is between the Tropic of Cancer and Tropic of Capricorn. Now, if we look at the distribution of surface temperature, we see that in northern hemisphere summer, so the land masses are hotter, much hotter than the northern hemisphere winter, and particularly over the Indian region, the northwestern part, the Sahara Desert and the Iranian plateau, and as well as there is a shift in the distribution of high temperature from the southern hemisphere to the northern hemisphere during the summer. So this is what speaks about the season, or say a long-term average, which means climate. So this is what we observe. So if we look at the daily variations, now what I'm trying to introduce to the audience here is that what is the difference between weather and climate. So this is a particular station in the mid-latitude, and here the black line depicts the day-to-day variations in temperature in that station. Okay, so what do you see here? In general, if you look at the green line, which is the long-term average or the daily climate, so it shows that summers are hot and winters are cold. Summer means June, July, August, and winter is December, January, February. However, if we look at the day-to-day variations, it follows this season. So a particular day in summer is hotter than a particular day in winter. Likewise, a particular day in winter could be warmer than a particular day in summer also. So that means these day-to-day fluctuations, they ride or they sit on the long-term average, which we call climate. Now, this is a particular variation for a tropical station, say Bombay. Here, the day-to-day variations in temperature is shown for 2 years. And here also you can see that summers are hot, winters are cold, but the day-to-day variations are like random fluctuations or instantaneous fluctuations or departures from the long-term average, or the which we call season, or which we call the long-term average or climate. So essentially, we can summarize that weather is what you get to see, or weather is what you experience, and climate is what you expect. So in other words, weather is the instantaneous state of the land, ocean, atmosphere coupled system, or the day-to-day fluctuations. Whereas climate indicates the mean state of the land, ocean, atmosphere system on which the day-to-day fluctuations of the weather rides. So here mean refers to say seasonal mean or long-term mean. So having introduced the concept of weather and climate, now let us try to understand what determines the climate of the earth. So you all are aware that the earth depicts two particular type of movement. One is called revolution around the sun, another is rotation around its own axis. Revolution of the earth around the sun in an elliptical orbit actually brings about the 4 seasons which we experience. However, this elliptic orbit or the eccentricity of the orbit has a periodicity of variation over 100,000 years. And what happens because of this is that the intensity of solar radiation reaching the Earth changes because of the distance of the Earth from the Sun. Apart from that, changes in the inclination of the axis of the Earth from the vertical, which has a periodicity of say around 40,000 years, which is also known as the obliquity, and the precision of the axis like a spinning top, which has a periodicity of about 23,000 years, 18 to 23,000 years. All these also bring about changes in the solar radiation. Now, solar radiation is the primary source of energy which drives all the circulations of the changes happening in the Earth. So how does it happen? So let us say the rays coming from the sun. I will digress here a little bit and introduce a little bit of mathematical equations here. So the rays of the sun coming from far away may be considered to fall on the Earth's surface almost parallelly. And what they see is only one side of the Earth, that is a circle. So now if the radius of the Earth is r, and S0 is the intensity of solar radiation falling on the top of the atmosphere per unit area, then the entire circle would get an energy of about S0 into pi r square watts. Now, if the reflectivity of the atmosphere is alpha, so global mean reflectivity or albedo is about 0.3 or 30%. So remaining 70% is the radiation that comes to the Earth's surface and heats the Earth. So S0 into pi r square into 1 minus alpha is what is gained by the Earth. Now the Earth is continuously rotating, so all the sides are getting heated up. Once it gets heated up, it starts radiating on its own like a gray body. So if the TE is the equilibrium temperature of the Earth's surface, then following Stefan-Boltzmann law, multiplying by sigma by the Stefan-Boltzmann constant, so sigma TE to the power 4 into 4 pi r square, which is the area of the surface of the sphere. So that would be the radiation emitted by the Earth. And if tau is the transmittivity of the atmosphere, means the atmosphere is like a medium and it will try to inhibit the transmittance of electromagnetic radiation. So let us assume that the transmittivity is 1. So if we equate these two on the both sides, on the left hand side and the right hand side, we would be able to calculate the global mean temperature of the Earth. And it turns out to be about minus 18 degrees centigrade. Now, is the global mean temperature of the Earth minus 18 degrees centigrade? Do you feel so? No, it's not. If it had been, then it would have been very difficult for warm-blooded animals living on the Earth. But the global mean temperature is not so, it is rather 15 degrees centigrade. So what is the reason for this difference of about minus 18 to 15 degrees centigrade? That is about 33 degrees centigrade. What causes this? So that is a result of the layer of greenhouse gases around the Earth. So what they do, it's like covering the Earth's surface, Mother Earth, like a blanket. It prevents all the radiation from escaping from the Earth and re-radiates back some of that. And the major greenhouse gases are carbon dioxide, methane, water vapor, etc. So greenhouse warming is actually beneficial, to be honest. What we have done anthropogenically is enhance the level of greenhouse gases around the Earth, and as a result of that, the global mean temperature has increased much more than what it should have been. So at present, because of the industrialization and other factors, the global mean temperature has increased by 1 degree centigrade than it was at the pre-industrial times. So because of the radiation of the Earth, because of the heating, more enhanced heating of the tropical region and more cooling near the poles, we have horizontal temperature gradient, which gives rise to pressure gradient. And because of that, we have uprising motion around the tropical region and sinking motion around the poles. So all the circulation features that we see in the atmosphere and in the ocean is because of this shape of the Earth, the tilt of its axis, its rotation, and the distribution of radiation on the Earth. Now, what are the components of the climate system? So there are basically 5 components. So it is constituted of the atmosphere, the hydrosphere, which includes all the water bodies, open, say rivers, lakes, ponds, say seas, oceans, etc. Then the frozen portion, that is the cryosphere, so it includes land and sea ice, so snow on the surface of the land as well as floating in the ocean. Then there is the Earth's crust, which is known as the lithosphere, and the 5th and most important component is the biosphere. So both the animals and the plant kingdom, they together constitute an important component of the climate system. And because of the mutual interactions between all these climate systems, what we get is the present climatic state of the Earth. So if we categorize, so we can have that external factors and internal factors that determine the Earth's climate. So what are the external factors which are actually natural variations? So these are the Milankovitch cycles. So the eccentricity of the Earth's orbit, the obliquity and the tilt, whatever I discussed in previously, that constitute the Milankovitch cycles. Then the solar activity, whatever, say sunspot activity or changes in solar radiation, meteorite impacts, they all are natural factors which determine how the radiation of the sun reaching the Earth changes. And then there are also natural variations like volcanic eruptions and changes in ocean circulation, which we call, although they are natural variations, but they occur within the Earth's components. So we call them internal factors, but these are natural variations. And other than that, the anthropogenic factors are the changes in greenhouse gases, tropospheric aerosols and all pollutants, then clouds, because the clouds, they affect the radiation budget. Then there is changes in stratospheric ozone content, and land use land cover changes brought about by the human beings. So together they determine the climate system and its changes. So now I would like to come to the later part of the present discussion and concentrate on the modeling of all these aspects. So what are the different type of models which we use to understand these physical and dynamical processes as well as the biological processes occurring in the climate system? So there are very simple models or box models which include only changes at a point. For example, the equation that I discussed to find out the global mean radiative temperature of the Earth is basically nothing but a zero order model or a box model. Then we have single column or vertical column models. These are called radiative transfer or radiative convective models. So they deal basically with all the radiation processes occurring in the Earth's atmosphere, and there are no boxes around these columns. So that means whatever horizontal processes are there, those are not considered, only vertical processes are considered. Then we may have two box models, one considering the processes occurring over land and another considering processes occurring over oceans. We can have multiple column models to slowly increase the complexity and the realism And then finally, we can have full-fledged three-dimensional models where we try to represent and simulate all the physical and dynamical processes occurring around the Earth, at the land surface, inside the ocean, as well as in the atmosphere. So out of this, there are basically, say, two types of models. So first, there are, say, global models which try to represent all the processes around the globe, and then if we want to focus on any particular region, then we try to use regional models or limited area models. The difference is that when we want to use a global model, then depending on our computational resources, for example, how fast our computers can do the calculations or how much storage spaces we have, then we may have to make some compromise, and we may have to choose data points at very far away positions. But if we want to do very intense calculations over a particular domain or a particular region, then we can choose data points much closer to one another, and then the computational resources won't be a factor at that time. Now, apart from that, so let us briefly discuss what are the fundamental physical and dynamical equations involved in modeling, whatever type it may be. So we have the momentum equations which deal with the conservation of momentum. So we have momentum equation along the east-west direction, along the north-south direction, and the vertical direction. So they deal with the movement of air under the impact of pressure gradient force, then Coriolis force, gravitational force, frictional force, etc. So these are the component-wise form along the east-west and north-south direction. Then we have the mass conservation equation. So mass would, mass is accumulating at some point. For example, if you all have witnessed tropical cyclones. So what happens? Spiraling winds converge over on the surface of heated ocean, and then the winds rise, and there is formation of cloud, and from that we have intense precipitation, and that is how. So that is a particular a result of mass conservation. So if the air mass is converging at some point, then it should then vent out. It should move upwards. If it is hot, it should move out. So this is what mass conservation deals with. Then there is energy conservation, which is taken care of by the thermodynamic energy equation, then the equation of state or ideal gas law, and finally the moisture conservation equation. So just like mass, you know that there is moisture which gets evaporated from all the water bodies present on the earth's surface, and as well as from the land in the form of soil moisture, and once it gets evaporated, then it goes into the atmosphere, and as it rises, then you know that the temperature in the atmosphere decreases with height. So slowly and slowly the air mass reaches a point of saturation, and then it starts condensing, forms clouds, and from there we get the precipitation. So these three momentum equation and the other four equations, that is in total 7 fundamental equations, are all that we have in all the models. What else we have is the way we try to solve these equations and the way we try to represent the physics in more and more detailed manner. That is what differentiates one model from the another, and the region that we choose for our study. Okay, so I will try to briefly touch upon what are the relevant processes in a climate model. So we have aerosols in the atmosphere, we have clouds, we have ozone, we have greenhouse gases, all that affect the radiation, and then in the surface we have ocean, we have ice and snow cover, we have vegetation, we have land versus water bodies, which affect the distribution of moisture and heat fluxes at the surface, and also the reflectance properties. Okay. Apart from that, when we try to deal with the oceanic and the interactions between the ocean and the atmosphere, then we try to do it in a very detailed manner, how precipitation changes the salinity and density of the ocean, and also that how the radiation fluxes get mixed up at the topmost layer, and oceanic processes gradually mix up the radiation towards the deeper layers. And then when we consider sea ice, floating sea ice, so you must have heard that there is a rapid melting going on in the Arctic and Antarctic region. So once this land ice breaks and it starts floating on the sea, then it has a remarkable effect on the salinity and density of the ocean. And all these also Apart from that, there is also biological activity occurring in this oceanic region in the form of phytoplanktons and other say water bodies and water animals and plants. So they all determine the exchange of carbon and exchange of heat fluxes between the water bodies and the atmosphere. Then we have exchange of the moisture and heat fluxes and CO2 and other gases in terms of exchange between atmosphere and land. So we try to consider presence of vegetation on surface and different layers under the soil, and then movement of water from the surface in the form of precipitation and then infiltration and then runoff at the surface and subsurface runoff. And then if there is presence of ice or snow on land, then the way the fluxes are exchanged, that would be different. And when we consider exchange photosynthesis, so you know that I mean you are more knowledgeable on this aspect, that so when there is exchange of gases, exchange of CO2, in order to perform photosynthesis in the presence of sunlight, the stomata have to open. But the vegetation is very smart. What it doesn't open the stomata so much that it loses a lot of moisture. If it loses a lot of moisture, then a suction is created, and then it tries to take in lot of moisture through the roots also. So the way they control this opening of the stomata and the gradient of moisture from between the soil and the roots, that also determines the suction, and that also determines the photosynthesis. So all these are taken into consideration while representing these physical processes in models. And apart from that, we have biogenic factors, say presence of vegetation, presence of how the agricultural distribution is considered and how they keep on changing, how there are formation of or distribution of evergreen and broadleaf forest and deciduous forest, and how they change, how they shed their leaf, and accordingly how the transpiration properties and the albedo keeps on changing. All these is taken into account. The exchange of carbon and other gases, that is also considered. So if I try to compile all this information in one figure, so this is what has been a remarkable figure which is produced by the IPCC, and it shows that in the mid 1970s what we had in these climate models was a simple atmosphere, a simple land surface, and ocean and ice, and we were happy with that. So the recent Nobel Prize in Physics which was awarded was given to that person who conceptualized this idea and showed that how carbon dioxide concentration can lead to enhanced warming, and gave us a warning that it could lead to further climate change also. So gradually more and more components were added. So in the first assessment report, aerosols, atmospheric aerosols were added. After that, in the second assessment report, carbon cycle was added. Then in the third assessment report, dynamic vegetation was added. Dynamic vegetation means normally what happens that vegetation changes from January to December, but on monthly basis. That is, only the leaf and stem area index would change from January to December. When there is precipitation or more rainfall, then the leaf area index would increase. Otherwise, during winter and the dry season, the leaves would fall and the indices would also decrease. But the distribution, the spatial distribution of the vegetation would remain same. Dynamic vegetation, what it does, that depending on the prevailing radiation or the existing temperature in the atmosphere or the humidity or the availability of other resources, the distribution of vegetation also would change spatially and automatically. So it increases the complexity of the model. And so obviously you can understand that if we have more computational resources, then only this kind of dynamic vegetation is switched on in the model. And in the very recent time, atmospheric chemistry, that is how these aerosols and pollutants interact with, say, acid rain. How do we represent it in the model? Or say other warm rain processes and cold rain processes. How do we incorporate it in models, in clouds? All this was incorporated in the last assessment report, which came out in 2013, the fifth assessment report, and land ice processes were also incorporated. In terms of computational power, since it has enhanced manifold, in India itself, we are running high performance computing resources at petascale. level. So you can see that when the first assessment report came in 1990, this is how the representation of land and ocean and orography was at a very crude level. So you could not differentiate that whether this is a hill or this is a part of a mountain. And the distance between two data points used to be around 500 kilometers. So imagine if you want to simulate whether there would be thunderstorm over Calcutta in the afternoon, and if your grid point space is about 500 kilometers, so instead of Calcutta, it might be occurring somewhere in northern part of West Bengal if we were still using a coarse resolution model at present. But slowly and slowly, not only our computational resources have enhanced, but our understanding of the physical and dynamical processes of the climate of the Earth, and as well as their representation in these models have also enhanced and become much more improved. So you can clearly see here, this is how the orographic region in the Alps, in the European Alps alpine region is represented. So this has enhanced. At the present time, the weather forecast system in India, which is being run by the India Meteorological Department, has a horizontal resolution of 12 kilometers. So it is very easy, and the forecast system that is adopted for tropical cyclone prediction is one of the best in the world. So you can easily understand that there has been remarkable improvement in this area. However, there are some more challenges. So one of the fundamental challenges is lack of observations. We still do not have very good observations in the atmosphere. We have very good observations over land, very good observations over ocean, and which has improved much compared to what it was around 50 to 60 years ago. But we still don't know appropriately how different atmospheric variables vary vertically. So that is one of the area. And then you must also acknowledge that there are different sources of errors in observations. So if we have accurate observations, we can represent these processes in a more better way. Now, here are two different figures. Both are same. Both represent something which is called radiative forcing. But this is a picture which is comparing radiative forcing of climate between 1750 and 2011. And this is between 1980 and 2011. So what is radiative forcing? That means what is the change in net surface radiation at the Earth's surface due to a particular component in the Earth's atmosphere. So you see carbon dioxide, other greenhouse gases, say methane, NOx, and halocarbons, and stratospheric ozone, stratospheric methane, surface albedo, aerosols, aerosol cloud. What is the change in surface radiative forcing due to these different components? Here, the shaded bar actually shows whether it is a positive radiative forcing and its magnitude, and the blue bar shows it is negative radiative forcing. So positive radiative forcing means due to presence of greenhouse gases, there will be increased radiation or increased temperature at the surface. And these whiskers actually represent the level of uncertainty. So at present, you see that we have more refined or precise information about the effect of the effect on radiative forcing due to these greenhouse gases, and the uncertainty level has also reduced. And even these are all the anthropogenic factors, and you see the level of uncertainty in the radiative forcing on the surface of the Earth due to different anthropogenic factors that has reduced dramatically. But still, there are some issues. For example, land use land cover change. For example, destruction of forests and the replacement by either bare land or crops. Does it lead to change in the reflectance properties more, or does it lead to change in surface evapotranspiration more? There is still debate on that. There are studies which show that in the tropical region, the effect on evapotranspiration is more, and there are studies which say that in the mid-latitudes and higher regions, the effect on changes in surface reflectance is more. But there are debates, and because of these debates, we still do not have a very accurate level of understanding about these effects. And there may still be other factors we still don't know, because all these components, their effect on different physical factors and meteorological variables, they interact with each other in a non-linear fashion. So that is what raises the level of complexity further. Okay, so with this, I would like to conclude the discussion here, and I would be happy to answer any questions from the audience.
Thank you, Dr. Halder, for a very enriching presentation. So there are a few questions that have come up. So let us start with those. So the first question is, can we differentiate between how much change in temperature is due to natural causes and how much is due to anthropogenic causes?
Yes, it is possible. So if we look at this figure, so let me first tell you that what these two curves actually represent. The top one represents the climate simulations, and these are all state-of-the-art climate models. They show the climate simulations of the global mean temperature of the Earth's surface, which include all the anthropogenic factors as well as natural variations, which I have discussed. And this particular graph shows all those results from all those climate model simulations, which include only the natural factors. This difference clearly shows that whatever change is there, the same models have been used with the same initial and boundary conditions, same equations, same physical and dynamical processes. So obviously, if you include a particular forcing in a experiment, and if you do not include that forcing in the same set of experiments repeated under the same conditions, then the result or the difference that you get, that can be attributed to the particular forcing. Now, why is there a particular shading here? Because we do not rely on only one particular climate model simulation. We do need multiple climate model simulations with the same model, as well as multiple simulations with different type of model developed by different modeling centers. So this particular shading actually gives us a standard deviation between all those results. Now you can see that the observed global mean temperature clearly follows those set of climate model simulations where both natural as well as anthropogenic factors were included. So this gives a very clear idea. However, this is a global mean picture. Now, if we look at this particular picture, here it shows the global distribution of 1 degree centigrade warming, and this is the simulated. You can see there is a remarkable similarity between these two plots. And there is something which is called polar amplification. That means there is enhanced warming in the polar region. This is because of the circulation in the atmosphere and circulation is in the ocean, that the enhanced warming in the tropical region is being carried towards the poles. And as you further do numerical simulations to see what would be the changes under 1.5 degree, 2 degree, and 4 degree centigrade warming, you can see that these changes depict a particular pattern. The land region get more warm, more hotter than the oceanic region. The particular reason is because the land has a lower heat capacity compared to moisture or water. So the ocean takes longer to get heated up, and the land gets heated up very faster. So if we want to differentiate, now suppose someone asks me, can you differentiate how much change in temperature India has witnessed because of anthropogenic factors and how much change has happened because of natural factors? That would be a very difficult question to answer, because in the atmosphere doesn't have any boundaries. So if I want to make a calculation for only the Indian region, I may have a lot of uncertainties, because there are interactions between different regions there, and these are non-linear in nature. So I may give you an answer, but with a certain level of uncertainty. And if we want to focus on more localized regions, the level of uncertainty will be more. But if we want to give an answer for a certain region, for say Africa or South Asia or say Europe or Russia or North or South America, then I would be able to give you a more better answer.
Thank you, Dr. Halder. The next question is, what is Indian Ocean Dipole and how does it predict Indian monsoon? And it has a continuation part. Can ENSO alone predict Indian monsoon?
Okay, this is a very good question. So, what is Indian Ocean dipole? So, look at this particular picture, which shows the pattern of precipitation distribution in northern hemisphere summer. So, if we take the sea surface temperature over east equatorial Indian Ocean, slightly south of the equatorial region, a box, and if we take a particular box depicting the sea surface temperature over west equatorial Indian Ocean, so the difference in temperature averaged over these two boxes is what is called, it is a metric that measures the strength of the Indian Ocean dipole. So the Indian Ocean dipole is actually a phenomena which is based on the change in sea surface temperature between the east equatorial Indian Ocean and the southeast equatorial Indian Ocean, and it becomes very strong during the later part of the monsoon season. And it is not very clearly determined whether the Indian Ocean dipole has a very strong influence on the Indian monsoon, because it is very inconclusive at present. The reasons are, the Indian Ocean basin is very, very small compared to the Pacific Ocean basin. So, during the monsoon season, different large-scale waves are generated. See, ocean is a fluid and atmosphere is a fluid. So, large-scale waves, which are called Rossby waves and eastward propagating Kelvin waves, these are generated. And the time these waves take to propagate from the western part to the eastern part and get reflected and then move eastwards, westwards again, is very short. So the IOD, there are studies which show that the IOD is a very important phenomenon during the monsoon. It has been found that during certain years when the ENSO is strong, the ENSO is the short form for El Nino and Southern Oscillation, which is a phenomena observed over Central and Eastern Pacific. So sometimes in certain years it has been found that the ENSO has a, primarily it has a tendency to reduce the monsoon rainfall. But in certain years, it has been found that the IOD, if there is an emergence of an IOD, then it tries to nullify, or sometimes it tries to add up to the effect of ENSO. But the relation between ENSO and IOD till date is not very clear, because it is a very highly nonlinear phenomena, and it becomes strong only towards the end of the monsoon season. It does not persist with equal strength through the entire monsoon season, that is June to September. Now, what is ENSO? ENSO is, see, there are two conditions. So, the rainfall band that you see around the equatorial region is a result of the convergence of the northeast trade winds and the southeast trade winds around the equator. So, when these winds converge, they converge moisture, the SST is very high, so the air gets heated up, the moisture rises, it leads to formation of clouds and rainfall. So under normal conditions, what happens? These easterly winds, they pile up the warm water over the West Pacific Ocean. So that is why you see more convection and cloud formation and precipitation over the West Pacific Ocean than the East Pacific Ocean. This is normal condition. So under, what is ENSO? What is El Nino condition? During certain years, there is a certain nonlinear phenomena in the atmosphere, because of which the strength of the easterly winds reduce suddenly. When it happens, when the strength of the winds reduce, then they are no more able to pile up the warm waters over the Western Pacific Ocean, and these warm waters, they start moving towards Central and East Central Pacific. Now, when the convection would naturally happen over West Pacific Ocean, the warm air that would rise here, then they would move along the east and along the west, which is called a Walker circulation, east-west Walker circulation, and then they would sink over the northwest part of India and Africa. However, when the center of convection moves towards the Central and East Central Pacific, as a result, the rising air and then the sinking part of that rising air comes over the Indian monsoon region. This is the reason why that if there is a strong El Nino condition, then it reduces the cloudiness and rainfall over the Indian monsoon region. Now, it has been found that around 40%, 40 to 45% of the interannual variation of the Indian monsoon is controlled by the El Nino Southern Oscillation phenomenon. And the ENSO is the single strongest phenomena or the climate mode which controls the Indian monsoon variability. Other than that, the North Atlantic Oscillation, which is actually a seesaw pattern in sea level pressure over the North Atlantic Ocean, it has been found another climatic mode which controls the rainfall, but towards the later part of the monsoon season, say July, August, and September. But beyond this, there aren't any other dominant climate modes which control the Indian monsoon. And the reason is that because of the typical distribution of the land versus ocean here, you can see that the Indian Ocean and the Arabian Sea and Bay of Bengal are bounded by land on three sides. And there is the Himalaya, which is acting like a wall, which prevents the cold and dry air from penetrating into the Indian region. And if the Himalayas were not there, then the cold and dry air would have reduced the convective instability, and that would have reduced the strength of the monsoon and rainfall. So apart from ENSO controlling about 40 to 45% of the Indian monsoon interannual variability, there is no other dominant climate mode. So I hope I have answered your question.
Thank you, Dr. Halder. Next question is, how do we predict El Nino and La Nina? And if El Nino condition prevails in Peru, how long does it take to reach India?
So as I said, the El Nino is basically the warming of the sea surface temperature around central and east central Pacific. So normally the El Nino peaks or reaches its strongest position around the winter season, and it has a aperiodic variability. So it has a life cycle that ranges from 3 to 7 years. It is aperiodic. Sometimes it may persist for 2 seasons or 3 or 4 seasons, and sometimes it may return back after, say, 5 or 7 years. So because of that, it is very difficult to predict. But with the present day computational power that we have, the knowledge and the observational system that we have, it is possible to predict the evolution of a El Nino correctly around 9 months earlier. Secondly, you asked about the climatic phenomena around the Peru coast. When under normal conditions, you see, you have the easterly winds. So when there is the opposite phase of El Nino is called La Nina. Okay. So when there is a La Nina, that means if there is a sudden increase in strength of the easterly winds around the equator, so what they do, they try to move the water from the eastern Pacific to the western Pacific. So obviously you can understand that there is a few meters difference in height of sea surface between western Pacific and eastern Pacific. So height of western Pacific is slightly higher than eastern Pacific. And as it tries to move the water, so since there is a boundary, see the North and South America, they create a boundary here. So cold and nutrient-rich water comes up from the deeper layers up to the surface. When that happens, in the presence of nutrient-rich water and in the presence of sunlight, there is phytoplankton bloom around the Peru coast. And the sardines and anchovies and all the other fishes, they thrive on this phytoplanktons, and there is also a bloom in the fish industry. So the economy of these coastal South American nations is highly dependent on this fish industry. And this is how the variation of El Nino and La Nina is much affects their economy, because when there is an El Nino, then the wind strength decreases and warm waters move towards the East Pacific. As a result, the upwelling or the upward movement of nutrient-rich water completely reduces. So there is a reduction in the phytoplanktons and the fish production there. So this is how they are related.
Okay, so the next question is, we have seen that the most important component for living is soil. And this is also used in construction. And so the proportion of this soil is decreased very much. How can we retain it?
I probably didn't understand the question. Can you repeat it again?
I think it's related to soil conservation.
Yeah, I can understand.
We have seen that the most important component for living is soil, and it is also used in construction. So the proportion of this soil is decreased very much. So how can we retain it?
So are you if you are speaking of reduction in soil content in certain areas, then it is a very alarming factor. So one of the methods how soil conservation can occur or soil enrichment can occur is plantation. Because if you do plantation, if you are able to grow forests and plants, then they help in the prevent the erosion of soil during precipitation, and they also help in enrichment or nourishment of the soil. So that is one way. And secondly is obviously we have to be very aware regarding soil conservation. We have to be aware in prevention of pollution of soil also.
Okay, thank you. So the next question is, what is the role played by MJO to influence Indian weather system?
Yeah, this is also a very interesting question. MGO or the Madden-Julian oscillation is a phenomena which is observed mainly during the winter season. So it is a eastward propagating Kelvin wave which originates over the west equatorial Pacific Ocean, and it moves like a Kelvin wave. The equatorial region acts like a channel, and Kelvin waves require a boundary wall to actually propagate. So it propagates like a wave of alternate convection and subsidence, and it moves and crosses the Indonesian archipelago and moves over West Equatorial Pacific and gradually decays. So it is most intense during the winter season. So it doesn't have a very strong impact on the monsoon as such. But during the summer, the MGO has a northward propagating component, which is known as the MESO. So the MESO or the monsoon interseasonal oscillation is actually a brother of the MGO, which becomes dominant during the summer. So when the MGO decreases in amplitude or its activity, and it is the MESO which takes over, so what we see is continuously propagating bands of cloudiness from the equatorial region over towards the land from southwest to northeast direction. And associated with this cloudiness, we have precipitation and rainfall activity. So when this band of cloudiness starts moving, so you can see that this precipitation band which we see here around the equatorial region is called the ITCZ, or the Intertropical Convergence Zone. So the winds converge moisture around the tropic, between the tropics, and it is called Intertropical Convergence Zone. Now it has, see, around the entire globe, it is located very close to the equator. But it is interesting that only over the South Asian monsoon region, it has two preferred locations. One over the equatorial region, another over the Indian landmass. So this suggests that this ITCZ continuously propagates from the equatorial region towards the Indian landmass. So when this region of cloudiness and rainfall is located over the Indian landmass, right over the monsoon trough, which extends from the northwest of India, Pakistan, moves through the Indo-Gangetic plains up to the headway of Bengal. When it is raining heavily here, then there are clearer skies over the equatorial ocean. And this periodicity of these northward propagating rainfall bands is about 30 to 60 days. Okay. And once it rains heavily and continuously for a few days, then it moistens the soil, the atmospheric instability decreases, and then cloudiness dissipates, and it moves to the foothills of the Himalayas and peninsular India. Then another band of cloudiness starts forming over the equatorial region, and then after about 30 to 60 days, after about 15 days, which is the half period, then it starts moving again over towards land. So this alternating episodes of northward propagating cloudiness and rainfall bands constitute the monsoon interseasonal oscillation, or MESO. So if the NGO activity is very strong during this summer monsoon season, then we won't have much rainfall activity over land. But if the NGO, that is the eastward propagating component, decreases, and rather we have the more of the northward propagating component of cloudiness and rainfall, then we have a lot of rainfall over land during the monsoon season. So these alternating episodes of rainfall and then clear skies and no rainfall activity, again another period of rainfall. So these episodes are called active and break periods. So depending on the periodicity of continuous rainfall, we may have 2 to 3 active periods or more than that during a good monsoon year, and during a drought year or bad monsoon year, we may have fewer active rainfall periods or episodes.
Thank you for a very detailed discussion. So the next question is, how will rising global temperature affect the ocean currents?
See, when the global temperatures are rising, it means that the temperatures are rising both in the equatorial as well as in the higher latitudes. So if we look at this temperature, this is between 50 degree north and south. It doesn't discuss what is happening beyond that. But because of this, if the tropics become warmer compared to the poles, so the gradient of SST between the tropics and the poles would reduce. And that would lead to a reduction in the rate of heat transport from the equatorial region towards the poles. This is very important. If you have all been fortunate to watch the movie which came out in 2012 when Al Gore received the Nobel Peace Prize, then you must have noticed that there is a transport of heat from the equatorial region towards the poles. This is being done by the atmosphere as well as by the ocean. And once these hot waters they move towards the poles, say over the North Atlantic, so what happens that when it reaches this colder region and the ocean is warm, then it starts evaporating. And once it starts evaporating, it becomes denser because there is also salts are there. So it becomes cold and it becomes denser. And when they become denser, then the water sinks. So when it sinks to the bottom, it leads to formation of deep water. This is called deep water formation. So this heavy or deep water that forms reaches the deeper levels of the ocean. And after that, once they reach the ocean floor, they start moving towards the equator. And a part of that again comes up around the equator. I discussed the phenomena of upwelling around the Peru coast. So where does this water come from? It is the deep water which comes from the pole through the deeper layers. And a part of that also crosses over and moves to the southern hemisphere. So there is an ocean circulation that happens on very, very slow time scale. And this particular phenomena of the ocean transporting heat is called the global conveyor belt. I do not have an appropriate picture of the global conveyor belt or ocean circulation right now, but that would have helped you understand this thing better. But this global conveyor belt is very important to redistribute the enhanced heat which is happening over the equatorial region, and this is required. Unless the heat gets transported, it will not affect the circulation and temperature distributions properly. So the global conveyor belt or the rate of heat transport would get slowed down, and that would affect all the phenomena, the convective phenomena occurring, as well as the biological productivity occurring in the ocean.
Thank you for the explanation. So we have the last question now. Does climate change have any direct effect on the emergence of epidemics and pandemics?
Yes. One of the easiest examples to give is the example of mosquitoes. So you saw that global warming and climate change are two different things. Global warming, I hope you must have understood from my discussion that a part is natural, and beyond that, what we have done, that is anthropogenic. So that is global warming, natural and enhanced global warming. And then there is climate, and then there is climate change, which is also brought about by natural and anthropogenic factors. So consider a mountainous region. So the higher altitudes of the mountain are colder than the lower altitudes. So obviously, the warmer regions or warmer fetches of the mountain, there would be more incidence of mosquito and growth of mosquito larvae and their activity. Now, because of warming and because of, say, regional and local climate change, higher and higher altitudes of the mountain would be experiencing above normal temperature. So the incidence of growth of mosquitoes and different mosquito-borne diseases, okay, so those would also increase as the temperature would change. So this is one of the easiest example. Then there is changes in precipitation. So what has been happening because of this climate change is that instead of having continuous episodes of rainfall occurring at a continuous rate, which we are used to see during the monsoon season, we are having short periods of extreme or heavy rainfall event. So the frequency and intensity of extreme or heavy rainfall events have increased manifold, whereas the low to moderate rainfall events, particularly if we speak about the Indian monsoon season, have reduced drastically. So when there is enhanced rainfall activity occurring over a short rainfall period, then the chances of the rain to penetrate into soil is less, and there are more chances of waterlogging and more chances of runoff also. So if the drainage system of the city is not well planned, it is very old, so there is more waterlogging, and more waterlogging, you can easily guess that there is more incidence of mosquito growth of mosquito. So these are direct examples. So the increased prevalence of say malaria and dengue, these are connected with the changes in climate. So if you want to do a correlation or a long-term trend with temperature and rainfall statistics over a few stations, and if you have the data, appropriate data, then you can get very good results. And there are other effects also. So for example, increase in pollution, so and aerosols, that has led to increased respiratory diseases and problems to vision. So everything can be done. A lot of data is available in public repositories, and if you want to do an analysis, you will get very good results.
Thank you for the detailed discussion. So there are no further questions. So thank you once again for a very enriching talk, and I enjoyed the discussion part as much as the talk. So before ending, I would request our head of the department, Dr. Mala Bose, to deliver the vote of thanks.
Good evening to all. We spent an enriching evening with Dr. Subhadeep Halder. Thank you, Dr. Halder, for your insightful talk.
Welcome.
We came to know about various types of climate models, hierarchy of climate models, processes related to climate models, what is increasing resolution of climate models, and the challenges facing in modeling, climate change and epidemics and the loss. I am sure it gave everyone a lot to think about. On behalf of the Department of Zoology, I express my heartiest thanks to Dr. Halder. Thanks to our principal madam, Dr. Urmila Ukil, for her encouragement and support. I would like to express my special thanks to our IQAC coordinator, Dr. Sudeshna Chatterjee. Thanks to all the participants of today's webinar who have joined from different universities, colleges, and institutions. Although we come from different states and countries, we are from one earth, our only home. Thanks to my colleague friends who are always with us. Our heartiest thanks and love to our students for active participation. Thanks to the joint convener of the program, Dr. Aniruddha Mitra and Dr. Kabiri Datta. I am also very much thankful to all the organizing committee members for making the event successful with your contribution. Thank you, Tamogno, for providing us the technical support. Finally, I would like to thank all of you present here for making the time to be with us today and make this event a grand success. Thank you and goodbye.
Thank you, ma'am.
Thank you, ma'am. So this brings us to the end of the event. So I would like to remind the participants once again that please fill up the feedback form, the link that has been provided in the YouTube comment section, as well as here in the Google Meet. And after filling up the feedback form, you will receive the participation certificates within a few days. So we will send it to you by email. So that was all. So we had a very nice, enriching evening today. So thanks once again to Dr. Halder for sharing his valuable time with us and enriching us. So we hope to look forward to more such experiences in future. Thank you, everyone.
To hear you again, Subhadeep.
Thank you, ma'am. The pleasure is entirely mine. And if not the technical problems were there, I think we would have been able to discuss for much longer.
No, that is not a matter. It can happen anytime, anywhere. Thank you.
Thank you, ma'am.